Hello, this is multivariable calculus lesson number 1, the shell method. Now actually, it's not multivariable yet. What we're first going to do is review some of the BC topics that are no longer on the BCAP exam, but they would be in a college course. So before we begin the new lesson, let's review the integral as an accumulator. For example, if we have a function drawn that's the derivative of another function, then the area of that little rectangle you see there is f prime at that particular point times the width delta x. And so the area, if we had a lot of little rectangles filling up the whole area from A to B, would be the summation of the n number of rectangles, the heights f prime times the width delta x, which morphs into the integral from A to B if we use instantaneous dx instead of delta x, where delta x goes to 0, and then we can write f prime as df dx, and so the dx's cancel, and what we're really doing is adding up all the little changes in f, not f prime, but the little changes in f, the antiderivative of whatever is graphed. And so what we get is the sum of all the little changes, which is the total change in f of x, the antiderivative of whatever function is drawn. And so of course we need a starting point. We need an initial value at a in order to figure out an actual function value. What we get from the integral is not a function value, it's the total change in the function. Another application we saw was when we did volumes. We rotate this region around the x-axis, and then we have infinitely many infinitely thin circles, and so the volume is the area of the circle times the instantaneous thickness, and so again we accumulate all the little tiny infinitely thin volumes to make the total volume. And so we think of the integral as an accumulator. Now we're going to look at a little video and then we'll come back to some more examples. Hello students. Our first lesson is going to be volumes by using the shell method that was skipped because it's no longer on the BC AP curriculum. But it's an important idea, and so that's what we're going to start with, things that the BC curriculum used to have but no longer does. So let's say we have a region like this. If we rotate it around the x-axis, there's no problem because we just have nice little discs. But if we rotate it around the y-axis, we have a little problem. Well, there's a hole in the middle, which we could take care of with washers, but we're going to be subtracting the same function from itself. Now you could, with a great deal of difficulty, solve for two different functions, one with a positive square root, one with a negative square root, and do it the old way. But this way is much simpler. Plus, what if you had a fourth degree polynomial that went and made two humps, and you wanted to rotate that? Then you really couldn't do it, because you'd have two holes, and it would be just far too complicated. So this is a new way of doing volumes. So first thing we're going to do, same as we used to, is we're going to draw the faux area over here and put dots. And then you're going to imagine rotating it. Okay? Now I'm going to turn off the camera and do some things with some construction paper, and I'll be right back to show you how it works. Okay? Okay, here's my pathetic little model. Not to scale, because all those little loops should be perfectly round. Those are called cylindrical shells because they come all the way around the back of the whiteboard. And so you have all these little infinitely thin cylinders. And so the thickness is going to make the volume, and then we're going to have to figure out the area of each shell. So in other words, we're going to take it off of this side. Hold on, taking the black spots with me, sorry about that. Take all those off and hold them out straight. And what shape do you have? Oops. Well, that one fell off. What shapes are these? Huh? Oops, well they won't stay out straight. I need you guys here to hold them. I'm going to do this in class. I have students hold them out. So see, if you hold them out, all these little cylindrical shells, if they're infinitely thin, you can straighten them out like this, and they're rectangles. And what's the area of the rectangle? Well, it's the height, which is the function value, and then it's the the length is the circumference, because remember they come out the back of the whiteboard too. And so the area is just going to be the circumference times the function value. And the circumference is going to be the distance from wherever you revolved it, which would be the x value in this case. And so that's the radius, so it'll be just 2 pi r. Okay, so now we're going to look at an example on a PowerPoint. Okay, but that gives you the general idea of what's going on. Okay. So here's a better illustration of what I was trying to show you. I hung the whiteboard upside down so that the rectangles would straighten out. So what we're doing is we're taking the infinitely thin shells that wrap around the side of a cylinder, straightening them out, making them into rectangles with equivalent area, and then when we add up all these infinitely thin rectangular solids, we're going to get the same volume as we would have gotten from the shells. Here's another picture showing how they straighten out. So here's that same graph, and this time we'll identify the function as 4x minus x squared. We draw our faux area that we get when we rotate around the y-axis, and there's a shell, a cylinder, and so we're just using the outside of that cylinder, the cylindrical shell. And in this case, the radius of the shell is x, so we're going to use that in our computation for r. And then we're going to straighten that shell out, and we get a rectangle. And the area of that rectangle is the length that comes out towards you, which is the circumference of the shell, 2 pi r, 2 pi x in this case. And the height is just the function value. And so to get little volumes, the thickness is delta x, which morphs into dx when we have it infinitely thin. And so the volume then is going to be the integral from 0 to 4. Those are the two x-intercepts. So the area, the green area, goes from 0 to 4 on the x-axis. 2 pi x times f of x, which is the area of the rectangle, and then the instantaneous change along the x-axis to accumulate all those infinitely thin rectangular solids. And so I took the 2 pi out, multiplied x through times f of x, which makes it 4x squared minus x cubed. And then you can do that integral by hand, or you can do it on your calculator. Okay, so that was a fairly simple example. Let's try a slightly harder one. Here's another region, and this time we're going to rotate it around the line x equals 3. Here's what that function is algebraically. Negative x to the fourth plus 2x squared plus 8. There's your faux region and the cylindrical shell. Now this time the radius is not x. The radius is going from the line to the graph. And so it's 3, which would be the distance all the way from the y-axis, minus the x value, which is the distance from the y-axis to the curve. So our radius this time is 3 minus x. We straighten that shell out, and notice that we always straighten it out onto the original area. And so now we have our volume equal the integral from negative 2 to 2, which are the x-intercepts. That's the region goes from negative 2 to 2. 2 pi r f of x. And in this case, we substitute 3 minus x for r. And we substitute negative x to the fourth plus 2x squared plus 8 for f, which gets really messy. So I just typed it into my calculator, leaving the pi out so that I get the exact answer. And then don't forget to put pi back at the end. So that one equals 179.2 pi. Here we have an area that's bounded by two curves. And we're seeing the backs of some of the shells here. Notice that the height of each shell is the distance between the two curves. So you're going to have to subtract the bottom curve from the top curve to get the heights. And in this case, the radius is x. That's going to become more complicated too. Now here you have the fronts of the shells being filled in, and so you can kind of see what the solid would look like at this point. Here's the backs again. R is x. The heights are f1 minus f2, the difference in the two y values, which you would have to express in terms of x in your integral, because since we're going around the y-axis, your integral for shells will be in terms of x. When we rotate around a horizontal line, our integral is in terms of y. Okay, so let's move on from this beautiful picture. Okay, so now let's compare the two methods, the previous method that you learned, discs or washers, to the new method of shells, just briefly here. So here we have a typical disk, and notice that the volume is pi r squared, and it's dx because if this disk was solid, the thickness would be along the parallel to the x-axis. So we integrate with respect to x, so that's dx, and we're going from a to b along the x-axis. Pi r squared is the area of the top of the disk, the circular cross-section, and r is y. And then if we wanted to integrate this, we'd have to change y into an expression in x. Okay, now let's look at the same picture, this time using shells. Now if this shell was made out of paper, the thickness of the paper would be parallel to the y-axis. And so we're going to integrate with respect to y. And the formula is 2 pi r h. In this case, r would be a y, and h would be whatever the x value is at that line minus the x on the curve, and then you'd have to rewrite that x in terms of y. Okay, so notice that when we revolve around the x-axis, disks use x to integrate, but shells use y, so it's like the opposite. Okay, so let's just summarize that. Rotating around the x-axis or a horizontal line, the disk washer method will use dx, whereas shells will use dy. Now what about if we rotate around the y-axis or a vertical line? What would happen? Well, we're not going to show you a picture, but obviously everything gets switched. So this time the disks and washer method uses dy, whereas shells use dx. Okay, so that's just a little summary of the difference between the two methods and setting up your integral, which is kind of important. You got to set that integral up correctly. Okay, so here's another example. We've got the graph of y equal x squared, bounded by the x-axis and the line x equal 2, and we're revolving it, that area, that gray area, around the line x equal 3, and so the faux area or the reflection is dotted. And then I have drawn a typical shell sort of in the middle of the solid. Notice that the height is y, which is x squared, and the radius is a distance from the line to the curve, which would be 3 minus x. Okay, so our integral would be 2 pi rh dx from 0 to 2, and we just multiply r and h together in order to integrate it. And I didn't show the antiderivative, but that's pretty simple. Okay, and that comes out to 8 pi. Now notice that if we did it the old-fashioned way, it would be a washer, and it would be big R squared minus little r squared, and we have to do it in terms of y. And big R then is 3 minus x, which would be 3 minus root y, since y equals x squared. And then the little radius, the hole in the middle, is always 1. And if you integrate, multiply that out and integrate it, you also get 8 pi. So again, I'm comparing the two methods, and in this case, I think you can see that shells is slightly easier. Okay, here's another example. We have, we're rotating around the line x equal -1, and the function is that parabola on the right, y equal x squared minus 2x, and the area is also bounded by the x-axis, the area that we're revolving. Okay, so if we tried to do this the old-fashioned way with washers, we have this little problem, because the outer radius goes to the same curve as the inner radius. Now you could do it. You'd have to solve for x by completing the square and then get two different functions for the two different halves of the parabola in terms of y, but it would be really messy, so we're not going to do it that way. Instead, using shells as shown, the radius goes from the line at -1 all the way to the graph, so it's 1 plus x. That's going to be your radius, and the height is just going to be the y value on the original parabola. Okay, so our formula again is 2 pi rh dx in this case. since the thickness of the shell would be in the x direction, and we're revolving around a vertical line, so we're using, we would be using dy the old way, dx this way. And then so we've got the radius 1 plus x times the height, x squared minus 2x, and you'd have to multiply that out, collect like terms, take the antiderivative, and evaluate from 0 to 2. When we put 0 in, we just get 0, so just put 2 in, and there you go, 64 pi over 3. So here's another example. We have the area bounded by y equal log x, x equal e, and the x-axis rotated around the x-axis. And so this one is fairly easy to set up an integral using disks, because we just have pi r squared from 1 to e along the x-axis, where r is the y value, and in terms of x, that's log of x. Now the problem with this one is you can't really integrate that by hand. Now, fortunately though, if we type it into our calculator without the pi, I got 0.78281825, which I recognized as e minus 2. But now you're not always going to be able to recognize that decimal, are you? Okay. So let's take a look at the other method and show you that in fact it yields an integral that can be integrated by hand. However, it is a little bit more complicated. So here we have a typical shell. The radius is y, and the height is the difference between the line where x equals e and the x value on the curve. And we're going to need an integral in terms of y. So solving for x above, we know that on the curve x equals e to the y. Okay? So our integral is 2 pi r h, where r is y and h is e minus e to the y. And this time we're going along the y-axis, and so the original area extends from 0 to 1 along the y-axis. Now if we distribute the y, we have something that's integratable but not particularly simple, so let's take a look at that integral. Let's split it into two integrals. The first one is easy to integrate, getting e over 2y squared from 0 to 1, and the second one is going to need parts because you've got a product there, y times e to the y. So using integration by parts, we let u equal y, which makes du equal to dy. dv then is the rest of the integrand, e to the y dy, and v is e to the y. Now we evaluate that first little thing, e over 2y squared from 0 to 1, and get e over 2. And then by parts, we get, well, we're distributing the minus sign, so we get minus uv, which is y e to the y from 0 to 1, minus minus, which becomes plus the integral from 0 to 1 of e to the y, which is v du, right? Okay, so if we evaluate y e to the y from 0 to 1, we get e, and then we evaluate the antiderivative of e to the y from 0 to 1, and we get e minus 1 for that, and so the e's cancel, and then if we distribute the 2, we get e minus 2 and then the pi on the outside. So that's our exact answer, integrating by hand. So, you know, you choose your poison and you do it the way you want. Let's take a look at another example. Here we have an area shaded in green, bounded by the curves y equal x and y equal 0.25 x squared, or 1/4 x squared. Notice that they intersect at 4, 4. And so now we're going to revolve around the y-axis. So there's my faux reflection, and there's a typical shell. All right, so we need the radius and the height. The radius is just x, and the height is the difference between the two y values. The one on the top, the larger one, is x, and the lower one is 0.25 x squared. Okay, so that's a little different than some of the other examples, because now the height does not extend all the way down to the x-axis. So our basic integral is going to be 2 pi r h from 0 to 4 using dx, because the thickness would be parallel to the x-axis, or you can just remember that going around a vertical line, we use dx. And then r is x, and h is x minus 1/4 x squared, and in order to integrate that, we need to multiply that out, expand it, and then take the antiderivative and evaluate from 0 to 4. Simple, simple, simple. And so we get 16 pi over 3. So it's just a little bit different setup, and in order to set these up correctly, I think a quick sketch really helps, and so I encourage that. Now notice that this problem could have been easily done with washers as well, but this lesson is about shells, and so for these last two examples I'm just going to do the shells method. Okay? Alrighty, let's look at another one. Let's look at the area bounded by y equal x squared and y equal x. So that's that green area there, and let's rotate that around the line y equal 2. Okay, so there's my reflected area across the line, and here's a typical shell. Notice that the height extends from one curve to the other, so the height's going to be the difference in the 2x values, because the height is always parallel to the line of rotation, and in this case we're going to have to subtract the x values to get that height. Okay, now there's the radius. This time the radius goes up and down, so the radius is going to be 2 minus y, because it doesn't go all the way down to the x-axis, so we have to subtract off the y value from that entire distance of 2 from the x-axis up to the line. Now, which variable are we going to be using? Well, the thickness would be parallel to the y-axis, or you can just remember, because we're rotating around a horizontal line, we have to use dy. And so our limits of integration have to go along the y-axis, which in this case our original green area starts at 0 and goes up to 1. So our limits of integration will be 0 to 1, and then we're going to put in 2 minus y for r and x2 minus x1 for h. And since we're integrating with respect to y, we have to change those x's into equivalent y expressions. And x2 is the curve furthest to the right, which is the parabola. And so for x2, we're going to solve for x up there in the y equal x squared, and then x1 is just going to be x, the other value. So there's our new integral in terms of y, and this slide's getting a little bit crowded. Oh, by the way, notice that this also could easily be done with washers, but I'm just going to continue with the shells example since that's what's going to be on your quiz. Alright, so there's our integral. There it is multiplied out. You would have to change the square roots into powers of 1/2, take the antiderivative, plug in 1 and 0 and subtract, and there's the exact answer, 8 pi over 15. Now, if you use your calculator, if you wimp out on any of these and use your calculator, I recommend you leave pi out and then use your frac button to get an exact answer and put pi back in. Okay, so there you have it. That's the last example for today. How something appears is always a matter of perspective. So whether a particular problem is going to be easier with discs, washers, or if it's going to be easier with shells is sometimes a matter of opinion. But on the quiz, of course, if it's a quiz on shells, then we're going to want you to use the shell method. But if you like, you can always check by using the disc or washer method. See you later. Bye-bye.